Okay, so hi everyone, welcome back from spring break. Today we're just going to go through the solution video for our 6th quiz in the course, which dealt with some acid-base thermodynamics questions. So we're going to study today the reaction between pyridine and aniline in aqueous solution, and we're given some of the thermodynamic data. We're given the pKa's and the proton affinities, and asked to answer a couple of questions. So let's jump right into this. So the first thing we have to decide is whether the reaction between pyridine and aniline is going to be spontaneous as written in aqueous solution. So many of you attack this problem by using the data given to figure out the delta pKa, and that's the right way to think about this. But you have to make sure to set it up in the right direction. So the delta pKa is going to be the pKa of the product, that's aniline, minus the pKa of the reactant, that's pyridine. And if you do the math out, that comes out to negative 0.6. Okay, so two things about this value. One, we see that this value is small. So we can conclude that it doesn't go to completion. However, whether or not the reaction goes to completion doesn't have anything at all to do with whether or not it's spontaneous. And for that matter, whether or not a reaction is fast or slow has nothing to do with whether the reaction is spontaneous. All we care about is whether the reaction is going to be exothermic or endothermic, and the sign of this pKa value tells us that. So when the delta pKa is negative, it doesn't matter what the magnitude is. If it's negative, then the free energy of the reaction is negative. So if delta pKa is less than 0, delta G is less than 0, therefore the reaction is spontaneous. Alright, so the correct answer for this question was that we do have a spontaneous reaction, and remember that has nothing to do with whether or not it goes to completion or what the rate of the reaction is. It just is the difference in free energy, or in our case we approximate that with the delta pKa between the products and the reactants. So when we find that that's negative, then we have spontaneous reaction. Okay, so part A down, moving on to part B. So which of the 4 species in the reaction has the largest free energy of solvation? Okay, so there was some confusion on this question because solvation sounds a lot like dissociation. So there's a little bit of confusion between those two processes. So it's important to really nail down which one you're talking about in this instance. And for me, when I'm confused about these things, it helps to write out explicit reactions that describe what I'm talking about. So for solvation, all solvation is taking some species A from the gas phase and putting it in some solvent. We're going to talk about water because that's what we mostly talk about in this course. So this reaction is solvation. So if I were to use the example of HCl, I'm going to take HCl from its gaseous state and put that into water and get aqueous hydrochloric acid, aqueous hydrogen chloride. Now, where the confusion came in was a lot of people were thinking, oh, well, I've got HCl, that's a strong acid in water, so I'm going to get lots of H+. Sorry, we're going to get HCl. Aqueous phase goes immediately and completely to H+, aqueous plus Cl minus, aqueous. This is not solvation. So this is not. This is a completely different process from solvation, and it's not described by delta G solve. So all we're going to worry about to answer this question is reactions that look like this. Taking something from the gas phase into the aqueous phase. So let's just cross this out. I just wanted to explain the difference there. Okay, so let's go back up and look at our choices, candidates for the best delta G of solvation. And when we're thinking about solvating in water, we've got HOH, right? So we know that water is polar. We've got positive charges, we've got partial negative charges. And we know that, so water is polar. And we know that water can do hydrogen bonds because we've got hydrogen bound to an electronegative element. So we've got H bonds. And it turns out that you can describe pretty much anything dissolving in water by using some combination of these two things. And we're going to do the same thing here. So let's look at our substrates and figure out which ones are going to best meet these criteria. So let's start with polar. That's the easiest one to think about. Water is polar. What does that mean? It means it loves charged substances. Water is really good at dissipating electrostatic charges. That's why you can dissolve tons of salt into water. So we can immediately eliminate pyridine and aniline from the list because they're neutrally charged species, and their cations, because they're positively charged, are going to automatically be better solvated than the neutrally charged species in solution. All right, so we knock out pyridine and we knock out aniline. So now we're given the choice between anilinium and pyridinium, which does not start with S. Okay, well, moving right along here, we've already checked polar off of our list. So now let's look at H bonds. In the case of pyridinium, you've got this Lewis basic nitrogen center, which can interact with the hydrogens on oxygen. But anilinium has that too, so we're going to say that those about balance each other out. With pyridinium, though, you've got one H bond, or one hydrogen that can participate in H bonds that's sticking out into solution from the aromatic core of the molecule. So pyridinium, we can say, will do one H bond. If we take a look at anilinium over here, we've got three nitrogens that are going to stick out in solution because this molecule is arranged a little bit differently. So this is going to have three potential H bonds. So because we get more potential H bonds in anilinium than we do in pyridinium, then we can say that anilinium is going to be better solvated in water than pyridinium will be. So let's summarize that down here. So greatest delta G solve belongs to anilinium, positively charged, good for polar water, and lots of H bonds, so more than pyridinium, sorry. Okay, so that summarizes the answer to this question here. And I just want to reiterate that we didn't take into consideration any of the acid-base properties of any of those species that we talked about. Because remember, solvation is just about reorganizing water around a molecule when it moves from the gas phase to the aqueous phase. So keep it simple and just consider one thing at a time. All right, moving on to the final question. Do you predict the gas phase proton affinity of ammonia to be larger or smaller than that of aniline? So again, we need to really nail down exactly what we're talking about here. So proton affinity sounds like basicity, but remember that proton affinity only exists in the gas phase. So let me circle that a couple of times here. Because again, a lot of the answers that we saw on this part of the quiz had to do with the solution reactivity, discussions of pKa's, and stuff like that. Remember that pKa is a solution-based equilibrium constant and is different from the proton affinity. And for the purposes of this question, we're only going to consider gas phase reactivity. So pKa is out the window. So let's draw the two molecules that we're going to consider here. We've got ammonia and aniline. All right, so these are looking pretty similar, right? Um, So when we're going to compare these two, we take a look and see if we can see any differences between them. Obviously, the only difference between these two molecules is this phenyl substituent on aniline that doesn't exist on ammonia. So what do we know about phenyl? So the pH group, if you remember from organic chemistry, is going to be electron donating. So if you have an electron donating phenyl group, that's going to push electrons out of the ring and onto this aniline, or onto this aniline nitrogen. And if we wanted to think about this in sort of a qualitative way, that electron density would kind of increase the size of this lone pair here, right? And again, if we were thinking about this just in like a back of the envelope quantitative way, we would say that because this lone pair is bigger, that it's more reactive and more reactive towards protons, so you'll get a stronger base, a stronger proton affinity that way. And that would be, almost right. So you get 1 point for claiming that the phenyl group is electron donating, and then that was the reason that aniline would have the higher proton affinity. But we can be a little bit more rigorous than that if we take a look up here. We're given the equation for proton affinity, right? So we're given the ionization energy of the proton affinity is equal to the ionization energy of hydrogen. That's the same all the time. The ionization energy of the base, hold that thought, minus the ionization energy of the base, just hang on to that, and then plus the bond dissociation energy between the base and the proton. Because these are both nitrogen bases, dBH is going to be about the same for both of them. And the dominating factor turns out to be the ionization energy of the base. So let's go back to our little sketch that we drew down here. We've got aniline. Aniline's got this big lone pair that was kind of inflated by electron density from this phenyl ring. And if we want to explain this in real thermodynamic terms, because this lone pair is bigger, these electrons are not as tightly held by the nitrogen, so it's going to be more easily ionized than ammonia will be. So because the phenyl group is electron donating, that means that the ionization energy for aniline goes down relative to ammonia. And then, again, take a look up here at the equation. If ionization energy goes down, therefore proton affinity for aniline goes up relative to ammonia. So just to restate, the gas phase proton affinity of ammonia is going to be smaller. So Pa, ammonia, Pa, aniline. Aniline is greater than ammonia. So the proton affinity of ammonia will be smaller than that of aniline, and the reason is because aniline has an electron donating phenyl group that increases the size of this lone pair, which results in a decrease in aniline's ionization energy, and because there's a decrease in the ionization energy, you see the proton affinity for that species go up. All right, so I hope that answers some of your questions, and as always, if there's something that isn't clear to you, feel free to find me in office hours.